Good afternoon. I hope everyone is doing well. And it's my great pleasure to welcome you to the second day of our tutorial series. And today we have a great speaker. I know Larry personally, in person since grad school, and I have been following his research since then. And it's my pleasure to introduce Larry today. So Larry is going to talk about today Stockpile, which is a Python package for inventory optimization and simulation. And I am actually using this package in my class this semester, in my class on inventory, and students are really enjoying it. Larry is the Harvey Wagner Professor of Industrial and Systems Engineering and Director of the Institute for Data, Intelligent Systems, and Computation at Lehigh University. Larry's research interests include modeling and solving problems in supply chain management and energy systems. His research has been published in leading journals and has been funded by the NSF, DOE, state agencies, and some other agencies. Larry, thank you for being with us this morning, and I look forward to your tutorial.
Thanks so much, Ebru. Thank you all for being here. So first of all, let's start with the name of this Python package. If you use Python, you know that every package has to have a cute name that has a PY in it. So it's Stockpile, pronounced just like the regular word, but spelled with a PY. So I started writing this package kind of ad hoc several years ago, partly as we were working on a graduate textbook that Max Shen and I co-authored. Don't worry, I'll show you the cover in a minute so that you can take pictures. And you know, as we were writing that book, I wanted code to be able to check the examples we were writing and the homework problems we were writing and that sort of thing. So I was just sort of accumulating little bits of Python, well, first MATLAB and then Python code that would solve the EOQ problem or the news vendor problem, or then the news vendor problem with some kind of variance, and then more complicated problems like multi-period dynamic programming type problems or multi-echelon problems. And I eventually realized that there was enough code there, and also that I really like writing that kind of code, and I decided to try to make like a, you know, robust enough standalone Python package that can do the basics of inventory optimization. I also do a lot of simulation of inventory, and that's partly because I find it to be a really useful way to just test out things that I'm not sure of. You know, if a student builds a model or writes some code and we're not really sure if the cost function is right that they derived or something like that, it's often really useful to be able to simulate the exact same system and see if the costs that you're getting from the simulation are really similar to the costs that we derive analytically, that kind of thing. So there's also a simulation component to Stockpile, but that's not a part of this tutorial. There is documentation online, but I won't really be talking about that part today. Today we'll mostly be talking about the optimization part. So Stockpile lives kind of on three separate locations online. PyPy is the place that houses lots and lots of Python packages, and you can download it from there. There's documentation on the website Read the Docs, which is where lots of Python documentation is, and the code is open source on GitHub, and you can access it from there. You don't typically have to access it from there. That's not how people would normally use this or most other packages. But for example, if you want to really see what's going on in a certain function, you can look there. And if you want to contribute to the project, I mean, it's an open source project, so if you think like, oh, I know of an EOQ variant that isn't in Stockpile and I'd like to write the code for that, there's ways to do that through GitHub as well. As I said, a lot of the models that are in Stockpile are in our book, Fundamentals of Supply Chain Theory. One is not a companion to the other. You don't need one in order to use the other. But I pointed out mainly because a lot of the notation we use in the documentation is the same notation as in the book. And you'll see even today that, you know, I'll give examples and stuff that are from the book. So I'll say, oh, this is example 3.4, this is problem 6.8, so that if you want to read the description of the problem in more detail, you can do that in the book. Just as a side note, with Karen Smilowitz, we're also working on an undergraduate version of this book that I hope will be out next year, although as Andreas knows, I've been saying that for about 4 years. But this time I really mean it, and so hopefully there will be an undergrad version of this book, and the Python package will, you know, play nicely with that as well. Okay, so my plan today is to try to do this in fully interactive mode. How many of you have laptops with you? Okay, so if you have your laptop with you and you want to follow along, you can take out your laptop. I'll give you instructions about how to access the software, and we're going to do this via Jupyter Notebooks. How many of you have used Jupyter Notebooks before? Okay, good. So a Jupyter Notebook, for those of you who don't know, is basically like an interactive way to run Python. So if you've done coding in Python or older languages, you're used to writing a big long script and then you press run and it runs the whole script, and if you've added any like print statements, then those things get printed. What's nice about Jupyter Notebooks is that you can have blocks of code that you run, and then the output of that code appears below it, and then you can run a separate block, and you can do it sort of piece by piece. And it also lets you intersperse code with other forms of communication. So you can have text, you can have images, you can have hyperlinks, and so on. So it makes a much richer, more interactive way of communicating about code. And so I really like it for this purpose, and I hope it works well today. Okay, so if you've used Jupyter Notebooks before, you might have run them locally on your computer where you have an IPyNB file or whatever it's called, and you launch it on your computer in a Jupyter Notebook. But instead, what we're going to use today is called Google Colab. How many of you have used Google Colab before? Okay, about half of you. So it's basically like a online version of a Jupyter Notebook. It's like a Google Doc type thing in the sense that it's online, it's free. You can collaborate with other people in a kind of similar way you can with a Google Doc. But maybe most importantly, they've already installed all the basic Python stuff. They've installed NumPy and Pandas and all the standard packages, and you don't have to install anything locally. So we're going to do that today. To get started, you should, on your laptop, if you're going to follow along, either go to that long address or that short address. They both go to the same place. Do I need to make it bigger? I have to admit, I was not expecting such a big room today, so I hope my font sizes are big enough. Okay, so when you get to, those URLs are going to take you to the GitHub repo for Stockpile. And in particular, they're going to take you to a subfolder that has these notebooks that we're going to use today. The notebook I want you to open is that one that says Stockpile Tutorial Section 1, Introduction. And when you click that, or double click it, you'll see something that looks like this. This is kind of a static version of the notebook. And you're going to click that button at the top that says Open in Colab. And then it's going to open up a version of it in Google Colab. Oh. Do you all have internet access? I just realized that. I hope you have some way of getting online, because otherwise this isn't going to work at all. Password is Amazon uppercase A for the Wi-Fi that's here. Okay, so once you click that Open in Colab button, it's going to open up the notebook in Colab itself, and it should look something like this. And I'll walk you through how this works and what you do. So let me just give you a quick overview of Jupyter Notebooks if you haven't used them in the past. Jupyter Notebook has two types of cells. So the document is divided into cells. And there's two kinds. There's text cells that just have essentially like plain text with formatting. And there's code cells. And in this screenshot, I've shown you the text cells. That's the first and the third cells there. And the code cells are the second and the fourth. The text cells are static. You could edit those, but there's no need to. But the code cells, you're going to be running. So when you run a code cell, it is running the actual Python, and you'll also be writing code today in those code cells. In order to run a code cell, you see those brackets in the top left of the cell. When you hover your mouse over it, it'll turn into like a little play icon, and you can click that and it'll play. If you're trying to do it right now, it probably won't work because you have to do something else first that I'll get to in a second. Or if you click on the cell so your cursor's in it, then you can press Control-Enter or whatever that curly thing is on a Mac and enter, and that'll run the cell as well. Okay? If you've used Jupyter Notebooks before but not in Colab, it's just the same in Colab. All right. So one other thing is that up in the top left, if you click that little menu-looking button, it shows you the table of contents for the notebook. So that makes it a little easier to navigate around the notebook. Okay, for those of you who just joined, if you have a laptop and you want to follow along, you can get started by going to tinyurl.com/stockpiletutorial. Okay, let's do it. So I'm going to shift away from the slides now and just shift over to Jupyter Notebook, which means I need my reading glasses. If you're in tutorial notebook number 1, I give you just sort of an introduction about the package. You can but don't have to read that now. Links to the 3 websites that I showed you earlier, the package on PyPy, documentation on Read the Docs, and the source code on GitHub. And then we're going to start by doing a few quick examples of how it works. So the first thing you have to do is install Stockpile. I told you that Google Colab pre-installs lots of packages like SciPy and Pandas and so on, but Stockpile is not quite enough at the big time yet that Google just automatically pre-installs it, but that's okay. In Google Colab, you can install any package you want. It's the normal command. If you've used pip install, you're going to pip install Stockpile, but inside Google Colab, you need an exclamation point at the beginning. I'm sure there's people in this room who can tell you why you need an exclamation mark. I don't know, but you do. So here's your first code cell to run. You're in the tutorial notebook number 1. Put your cursor in the first code cell, the one that says exclamation pip install Stockpile, and then either click the little play button or hit command control enter and it'll run the cell. And this should take 20 seconds maybe. It's going to give you lots of output. And if it gives you a warning at the end that says, oh, you have to restart your runtime, just ignore it. That's fine. Okay, now, Stockpile is now loaded into your Google Colab notebook, and you can import it just like you can import any other, like you would import any other package. You can do something like import Stockpile, and now the whole Stockpile is in memory, or you can import just individual modules or individual functions, and that's what we'll mostly be doing. So Stockpile is organized into modules. And I've just sort of grouped the modules logically here. There's a bunch of modules about single echelon inventory optimization. And if you've ever taken or taught a class on inventory, these are the models that you already know and love. EOQ, News Vendor, RQ, SS, Wagner-Witten. Finite horizon model is the stochastic dynamic programming finite horizon model, which is maybe that's like a little more advanced in inventory. And then there's a module with a bunch of different supply uncertainty models. There's also some modules for multi-echelon inventory. I won't go through the details of those now. Then there's a few modules for the simulation. As I mentioned, we won't talk about that today. And a few other modules that are just sort of like helpers. I'll touch on those a little bit. But for the most part today, we'll be talking about the single echelon inventory stuff and the multi-echelon inventory stuff. Okay? So let's do one. So the first problem we're going to solve is an EOQ problem with a fixed cost of 8, a holding cost of 0.225, and a demand rate of 1,300. This is example 3.1 in Fundamentals of Supply Chain Theory, which I just abbreviate FOSCT. So put your cursor in this code block and run it. And if you did everything right, oh yeah, okay. So one other difference between a Jupyter Notebook and Python, if you're running it, in VS Code or something, is that it's not automatically. Well, I guess this is true in VS Code too. Anyway, the way I've written that, it saves the outputs in Q and cost, but it doesn't tell you what those are. So in the next cell, I just say, tell me what Q and cost are. So run that one as well. And now it says that Q, the Q value that it returned, the optimal Q for that problem is 304.04 something. And the corresponding optimal cost, average cost per unit time, is 68.41. Okay, good. You just did your first Stockpile code. This is the basic idea. For most of the single echelon stuff, you have a function for each problem. You give it the data, it gives you the answers. One thing I'll point out is that, in the documentation, well, I'll get there in a little bit. We also have a module for News Vendor. So similarly, I'm going to run this News Vendor problem with a holding cost of 0.18, a stock out cost of 0.7, and normally distributed demand with a mean of 50 and a standard deviation of 8. After you run it and then ask it to give you the results, it tells you S, the base stock level or order quantity, is 56.6, and the corresponding cost is 1.9976. Okay? The functions in Stockpile mostly use longer, more descriptive parameter names. I went back and forth a lot as I was starting to code this on like, should I call the inputs to these functions things like h and k and alpha, because that's what we tend to use. But I decided in the end to just use more descriptive names because every textbook is different. And even though this means more typing, it's, I think, easier to use. What's that? Oh, you're welcome. But just like any other Python code, I mean, for this particular function, there's some parameters that are required, and you can just put them in the order that they go in without having to specify the name, like holding cost equals, or you can specify the names of the parameters. Yeah.
Maybe a little bit later, but the function in Stockpile, can you apply it to a pandas data frame directly, or do you have to go about that?
Okay, so the question was whether you can apply a function like this to a pandas data frame directly, or whether you'd have to loop through the data frame and apply it one by one. You cannot apply it to a pandas data frame, although I'm open to contributions to the project if anyone feels like adding that capability. But for many of the functions, I can't remember if this one works that way. For many of the functions, you can give it a list of values, and it'll return a list of corresponding solutions. So it can't necessarily handle pandas data frames, but it can handle lists. Okay. It can do Wagner-Witten. So this solves Wagner-Witten using the standard dynamic programming algorithm. The function Wagner-Witten in Stockpile returns 4 things. It returns a list of order quantities Q, the cost over the time horizon, called cost. In Wagner-Witten in the dynamic programming, you have this theta function, or it's called other things in other books, that returns, it's basically the cost to go function. So the output theta gives the values for that function. And also the way the DP works is you're basically deciding, if I order in time period 6, when should the next order be? Maybe that's 9. So the parameter S, the output parameter S, tells you for each period when would be the next optimal period to place an order. Okay? So after you run that, you can have it tell you. So in this case, the optimal order quantities are 210, 0, 150, and 0. Now let me make another comment here, which is that in most of the inventory treatments I know of, and certainly in our book, everything starts at time period 1. But in Python, everything starts at 0, right? All like arrays, lists are indexed starting at 0. So most of the time, you can enter the inputs in an array of length. Like if this is a 4-period problem, you can just tell me the demands in a list with 4 elements. You don't have to put a 0 at the beginning, even though really the 90 is there for period 1, not period 0. There is no period 0. But when it returns the values, it often gives you that extra 0 at the beginning, which you can basically just ignore. Probably that's something I should omit, but anyway, that's what's going on here. There's some flexibility in the way you provide values for a multi-period problem, and I'll get into that in a little bit. Okay, so there are the order quantities. The optimal cost is 1380. The cost to go values are these, and the next order periods are 3555, which means, remember, you always order in period 1. So in period 1, the next best order period is 3, so you order in period 1 and then 3. And then the next order period for period 3 is 5, which means you don't order again ever because it's only a 4-period problem. If that is not as intimately familiar to you as it is to me, that's fine. I teach this all the time, and so, I'm Wagner-Witten is part of my blood by now, and if you didn't follow what I just said, that's fine too. It's all written out in the documentation. Okay? All right. We can also solve finite horizon stochastic problems. Let's skip that for now. I'll get into that later. And then finally, we have functions for solving multi-echelon problems. So in multi-echelon, and I'll get into this in a few minutes, the world of multi-echelon inventory optimization tends to be divided into stochastic service models, that's like the Clark-Scarf type model, and guaranteed service models, that's like the Willems and Graves type model. And Stockpile has code that implements both. So the first problem here is an SSM type system. It's like a Clark-Scarf kind of system. And there's a couple ways to feed it the data, which I'll get into in a little bit. But in this little code snippet, I've told it, okay, I want to first build a network. It's going to be a serial system. It has 3 nodes, has these holding costs and these lead times and this type of demand, et cetera. I'll get more into details about what those things mean in a little bit. And then it builds a network object that I then pass into the function to optimize the base stock levels. And once I run that code cell, which is a little bit slower because there's more computationally intensive stuff going on in this function, it optimizes and then tells me the optimal base stock levels and the corresponding optimal cost. Okay. We also, as I said, have features for, let's see, what is this? Oh, okay, so this demonstrates the simulation. I told you I'm not, yeah, sorry, go ahead.
Just a question, maybe you come to this later, but in all the functions you showed now, you always use like parameterized function command. Is it also possible that I put in some kind of demand vector? And it's maybe parameterized distribution or...
Okay, so are you referring to where it says like, okay, this is normally distributed demand and you want different kinds of demand?
I mean, first of all, can I use different kinds or can I just use real data and then build some distribution?
Different kinds, yes, for most of these functions. You can, and I'll get to this in a little bit, some of them have a few built-in things like normal or Poisson. And then a more generic one where you can just give it a probability distribution like that you can build in SciPy, for example, and hand it that, and it'll solve based on that. If you want to give it demand based on real data, you probably have to build that as some kind of distribution object. Yeah. Other questions? Yeah.
So basically, multi-echelon inventory system, serial systems would be used for fouling, where you have a supply chain network consisting of different nodes, and you want to be able to tell what is the economic or quantity at each and every node, right?
So the question was, is this multi-echelon inventory? Yes, it is. It's a serial system. In this case, 3 nodes. One ships to the next, but it's not economic order quantity. So EOQ is a very specific kind of inventory model. This is a different specific kind, but you have the right idea. Yeah. Okay. So this next code block demonstrates the simulation, which I said I won't talk about too much today, but we'll at least try it. So what this is doing is saying, okay, well, first of all, we have an issue with echelon versus local base stock levels. If you've studied multi-echelon inventory theory, you've run into that issue. For now, just trust me that I'm doing the conversion that I need to do. I'm also telling it that at each node in the system, it's going to have a base stock policy. And then I'm going to simulate for 1,000 periods this network that I built here. Okay, so I'll do that now. And it's done. And then, for example, I can get the total average cost per period, 226. All right, but the simulation can give you much more detailed output. It can give you period by period, what are all the state variables and so on. All right, but as I said, like I like to use simulation as a way to double check optimization that I've done. And so, you know, here we optimized this system using Clark-Scarf type approach, and it told me that the optimal expected cost is 227. And then I simulated the same system and got a cost of 226 per period. So this is the kind of double check that I find really useful to do and is part of why I built the simulation part. All right. As I said, I implemented Graves and Willems DP algorithm for committed service times in GSM systems. Probably we'll get to that in a little bit, so no need to run that now, although you certainly can, it runs fast. Okay, I'm going to move on to the second notebook, which talks in more detail about the single echelon inventory stuff. Any questions before we do? Okay, so if you go back to the GitHub repo. Now click on section 2, single echelon inventory. Again, click on the link for open in Colab, and then you should find yourself here. Now the notebooks start to have homework for you, or have exercises for you to try as well, okay? So as I said before, we have EOQ, News Vendor, RQ, SS, Wagner-Witten, Finite Horizon, and so on. And we will, in this section of the tutorial, I'll cover the first batch of bullets. The last bullet about supply uncertainty is in the next section, okay? So you're in a new notebook now, which means you need to pip install Stockpile again. Each notebook needs its own install. So I've already done that, but oh, it looks like it forgot. So I'm going to do that again, and you should do the same if you haven't already. As I said, if you get that warning that just disappeared, you can ignore it. And while it's running, you see there's like a progress indicator. When it's done, it'll turn into a checkbox or check mark or something. So while it's installing, I'll just point out that for most of the functions that I talk about in the tutorial, I also link to the documentation. So like if you click this link for the economic order quantity function, it takes you to the documentation. First, it warns me that I'm leaving Colab. That's fine. So this is the online documentation, and it tells you, the signature of the function. In other words, what are the parameters that it's expecting you to provide? What do those all mean? In brackets is the notation from our textbook. So fixed cost is K, holding cost is H, and so on. You don't need to know that to use the Python package, but if you're trying to match up the code with examples in our book, for example, that's the sort of mapping. And then also what the output parameters are. The documentation usually gives the formulas that the code uses to calculate to do the calculations. It gives a quick example. Okay, so the documentation is relatively complete, and much of it is linked to from the tutorial, but there's more there that you can get to on your own. Okay, so this is the signature of the economic order quantity function. It expects you to give it fixed cost, holding cost, demand rate, in that order, unless you tell it there's a name for this, when you give it, like you tell it the name of the parameter equals, and then you provide it. Some Python experts in the room can remind me what that's called. Keyword arguments, thank you. You can provide it as keyword arguments and put them in any order you want, or you can give it in the order that it lists here, just like any other Python function. There's also an optional parameter called order quantity, which is if you just want to calculate the cost of an order quantity that you come up with, you give it the order quantity and it just calculates the cost. All right, so I'll show you how that works. You already did one, but this is basically the same thing. So first I'm importing the function and then running it on the same example as in the first notebook. And instead, if we wanted to say, okay, the optimal order quantity is 304, but suppose I want to give you an order quantity of 350, what's the cost of that? And it'll tell you that cost. All right, and many of the functions in the package have something like that. Okay, your turn. So here's your first exercise. Solve the EOQ problem with a fixed cost of 150, a holding cost of 2, and a demand rate of 200. By the way, when you loaded this, when you opened it up in Colab, you're using your own copy of it. It's not going to clobber anything that I wrote or posted anywhere. This is your own local copy, and you can do whatever you want to it, and it won't cause problems for anybody else. It probably gave you a warning when you tried to run the cells that said, like, whoa, Google takes no responsibility for this, and once you pass through that warning, you can go. So this is all you should have to do. Economic order quantity 150 to 200. You can pass the keyword arguments if you want. I didn't, because I know that it goes in order: fixed cost, holding cost, demand rate. And once you run that, you should get the quantity. Is this the same quantity that everyone got? 173 and 346. All right. And then the next exercise says, what if we want to use an order quantity of 50? And to do that, we just do the same thing. I know I'm jumping ahead here, but do the same thing, but add order quantity equals 50. Oops. And it tells me, okay, for an order quantity of 50, the cost is 650. Okay. The module has functions for a couple variants of the EOQ, like the EOQ with back orders or the economic production quantity problem. I won't go into details about that. It can also do a little bit with JRP, the joint replenishment problem. So this is the problem where you have multiple products and there's a fixed cost to just place an order, but also a fixed cost for each product that's included in the order. So you want to try to sync up the products so that you're not paying too many fixed costs. I just implemented one pretty simple heuristic for that. There's lots out there, and if anyone wants to take a crack at it, in case I hadn't mentioned before, I'm open to contributions to the project, so feel free. Okay, so we'll skip this part. All right, we have the news vendor problem. I'll just mention that I use the word news vendor even if it's like an infinite horizon problem. So normally when you describe the news vendor problem, you say it's a single period, right? The news vendor buys newspapers in the morning, sells them throughout the day, and then the period's over. The unsold newspapers can get salvaged, but they can't get saved until tomorrow. And if there's stockouts, you can't save those until tomorrow either, right? It's just a single period problem. But it's mathematically equivalent to the infinite horizon version of the same thing, where you can hold inventory from one period to the next with a holding cost, and hold demands, hold stockouts from one period to the next with a stockout cost. The math is the same, and so I tend to call both of them news vendors. I know some people find that to be sort of frustrating and confusing, and if you're one of those people, I'm sorry for that. But the news vendor module here solves either type of problem for the most part. Okay, so there's a function called news vendor normal that solves the problem with normally distributed demands. That one looks like this. So if we have a holding cost of 0.18 per item, a stockout cost of 0.7 per item, and a demand distribution that's mean of 50, standard deviation of 8, this is example 4.3 from our book, then this code solves that problem. You give it the holding cost, the stockout cost, the demand mean, the demand standard deviation, and when you run it, it tells you that the optimal order up to level or base stock level or order quantity is 56.6 and the optimal cost is 1.99. Okay? Similarly, you can tell it, okay, I want to use a base stock level of 60. What's going to be the cost? We'll skip that part. You can also give it a lead time. Normally, we assume the lead time is 0, but you can give it a non-zero lead time, and it calculates accordingly. Okay, your turn. Solve the news vendor problem with a holding cost of 3, a stockout cost of 16, and a normally distributed demand with a mean of 100 and standard deviation of 22. For those of you who are watching the video later, I know this makes for great TV while everyone is working on the problem on their own, but of course you can do the same. Okay, so this one's also pretty straightforward. Anybody have it already? Okay, so my code is news vendor normal. Holding cost is 3. Stockout cost is 16. Mean demand is 100. Standard deviation is 22. And there's our optimal order quantity and cost. Okay, so that function is for news vendor with normally distributed demand. There's a function that handles Poisson demand. It looks just like the normal distribution, but it doesn't have a standard deviation. Then, getting to your question from a few minutes ago, you can also give it, there are also functions that let you give it a very general probability distribution. So either a continuous distribution or a discrete distribution. In the case of a continuous distribution, so in SciPy, the kind of scientific computing package for Python, there is an object called an RV continuous object, which is like a generic random variable, a generic continuous random variable. And with an RV continuous object, you can create a normal random variable or uniform or exponential or what, all of our favorite kinds of random variables. It has built-in features to do that. Or you can just create a custom continuous random variable with whatever probability distribution you want. So you can create that in whatever way you want in SciPy and then get an RV continuous object out of that and pass it to this function called news vendor continuous. I also will mean to add the ability to just, you can write a function that just is the PDF basically. I give your function x, you give me f of x, but I haven't written that yet, so it's listed here in the bullet, but it hasn't been implemented yet. Sorry about that. Okay, so for example, if I want to solve a problem with a holding cost of 1, stock out cost of 0.1765, and log normal demand with parameters mu equals 6 and sigma equals 0.3, then we can use SciPy stats and import the function log norm, which gives you an RV continuous object. Okay, so in particular, I'm saying I want a log normal random variable with parameters 0.3, and okay, so it's a little annoying because the way log norm works in SciPy is if you want a log normal random variable with mu and sigma, sorry, that should say mu and sigma, then the first parameter gets set to sigma, that's the 0.3 here, and the second parameter gets set to 0, and the third parameter gets set to e to the mu. Okay, so I created the log normal variable that I wanted, and now I have that demand distribution as like an object, and I can pass it to news vendor continuous. And there's the result. Okay? And you can do something similar with discrete random variables. You can pass it an RV discrete object, which similarly is created in the SciPy stats module. Or you can give it a dictionary. So you can just give it a list of all the demand values and the corresponding probabilities. Maybe this is what you were asking about a minute ago. You can say, okay, this random variable has demand between 0 and 10. The probability of 0 is 0.04. The probability of 1 is 0.07, whatever. Okay, and build that into a dictionary and pass that to it. So in this example, I have a Poisson distribution with mean 6, holding cost 1, and stock out cost 4. So I solve it in two different ways. One is to just build the Poisson object as an RV discrete object and save that in a variable called demand distribution, and then pass that to news vendor discrete. And in the second way, I built a dictionary that gives me the keys are all the values between 0 and 40, and the values in the dictionary are the corresponding Poisson PMF values. So I get this dictionary called demand PMF, and that's what I'm passing to news vendor discrete instead. But I'll run both of these, and you'll see that the results are the same. So optimal order quantity 8, optimal cost 3.57, and the same if I build it the other way. Okay. So let me ask you, do you want to keep doing these exercises sort of live in the room here, or do you want me to just keep going and walk through the different features and you can stop me and ask questions and run the code on your own at home? How many people would rather keep doing code in class today? 1. And how many people would rather just sort of walk through the code? More than 1. Okay, let's just do that then. But I should mention that the same notebooks, but with my code, with the solutions effectively, are also stored in the GitHub repo. And so if you want to try to do these on your own, you can, and then look at the solutions if you get stuck. Okay, so, one way of describing the news vendor problem is using a holding cost and stock out cost, or equivalently like overage cost and underage cost. But sometimes when we teach the news vendor problem, we teach it with the 3 parameters: revenue, purchase cost, and salvage value, right? I buy the newspaper for $1, I sell it for $2, I salvage it for 50 cents, something like that. And we know that that's equivalent if you define the variables in the right way in relation to each other, but Stockpile also has a function to solve this so-called explicit form of the news vendor problem, where we have the revenue, purchase cost, and salvage value. There's a Poisson version. I think I don't have versions with generic continuous or discrete distributions, but if that's the situation you're in, then you can always just convert to the implicit form and solve it that way. Okay, any questions about news vendor? Great. The RQ optimization problem, remember, this is the type of problem where you have a continuous review, you have a fixed cost, so you have to decide both The order quantity to order each time, that's Q, and the reorder point R, that's what triggers the order. And this is a weirdly kind of more difficult problem than some others. So what is often taught are approximate versions of this problem. And there's a bunch of approximations out there dating back, 70 years or something. Probably the most famous one is the one that in the book we call the expected inventory level approximation. And this is the one where you wind up with two functions, two equations and two unknowns, Q and R, and you solve them iteratively. If you've learned the QR model in any kind of undergraduate class especially, this is probably the version you used. So there's a function that implements that approximation, and functions that implement a couple of other approximations, the so-called economic order quantity with backorders approximation, which approximates the QR model like an EOQ model with backorders. The EOQ plus safety stock approximation, where you think of it separately kind of as the EOQ part to find the order quantity and a safety stock calculation to find the reorder point. And the loss function approximation, which is a more accurate approximation, but much less well known. It dates back to Hadley and Witten in 1963, and it uses the so-called loss functions for the demand distribution. By the way, so if you're an inventory theorist, you know that a loss function is a characteristic of a demand distribution, a probability distribution. If you're a machine learning person, you think a loss function is something totally different, but you're wrong. What a loss function really is like the integral of the CDF, basically. But anyway, these days it's really hard to Google like loss functions, though, because all you get is machine learning type loss functions. Anyway, okay, end of rant. Okay, so I have functions to solve all of those. Now, these functions don't tend to return costs. They just return R and Q. But there's a function called RQ cost that lets you calculate the cost, and that's the exact cost. So there is a model that calculates the exact cost of any RQ that you choose, and so you can solve it heuristically a couple different ways and plug those solutions into the RQ cost function to be able to compare them. Okay, that's RQ. SS is similar. Remember, SS is a periodic review model usually. You're deciding the order up to level called capital S and the reorder point called lowercase s. Yes, it's annoying that they're both called S. It'll get even more annoying with the S's in a second, but bear with me. So you can solve that problem with discrete demands exactly using this function called SS. Oh, sorry, you can calculate the cost of any given S and S for a discrete demand distribution using this function. And you can also solve the exact model using the algorithm by Zheng and Federgruen from 1991, again for discrete demand distributions. In the book, we talk about solving it for continuous demand distributions, but that hasn't been implemented in Stockpile yet. There's also this kind of crazy and funny approximation called the power approximation, where you basically find S and S through this like closed form equations basically that have, anyway, okay, so that's in there as well. All right, any questions about RQ or SS? All right. So the next section is about how to specify time-based quantities. So for things like Wagner-Witten and finite horizon stochastic problems, you have to often give it like a vector, an array, a list, that says here are all the costs from period 1 through 10, or here are all the demand means from period 1 through 10. And as I mentioned before, there's a couple ways to do that. You can just give it a singleton, you just say 10, and then it'll use that value for every period 1 through 10. Or you can, or you can give it, where do we go? Or you can give it a list. So here's where the 0 indexing versus 1 indexing comes into play. If you have periods 1 through 10, you can give it a list with 10 elements, that's fine. You can also add a 0 at the beginning and give it a list with 11 elements, that's fine too. And the code will figure out which one you meant because you're also telling it how many periods are in the horizon. Okay, so I tried to make it flexible. In the guise of making it flexible, I probably made it more complicated than it needed to be, but that's anyone who knows me knows that that's pretty on brand. So if you want the holding cost to be 1 in every time period 1 through 3, then these are all equivalent. Just say holding cost is 1, or holding cost is 1, 1, 1, or holding cost is 0, 1, 1, 1. They all mean the same thing. Or if the demand is 10, 30, 25 in periods 1 through 3, you can give it that as a list, or you can add a 0 at the beginning and it doesn't matter. Okay? All right. So Wagner-Witten uses parameters like that. And here's an example. So remember Wagner-Witten, in the Wagner-Witten problem, you have discrete time periods, no uncertainty, everything is deterministic, you have a fixed cost and a holding cost, and your goal is to determine what periods to order in and how much to order in each time period. So the Wagner-Witten function implements that. In this case, I'm saying that I have 4 periods, the holding cost is 2 per period, the fixed cost is 500, and the demands in the 4 periods are 90, 120, 80, and 70. It solves very fast because it's a really fast algorithm, and these are the resulting order quantities and cost. Okay, same as we looked at in the first notebook. Yeah, we'll skip that. Okay, and then there are these stochastic finite horizon problems, which are not typically covered in like an undergrad course on inventory, but would be often covered in a grad course, where you have a dynamic programming recursion, but the demands are stochastic. And that, that model is implemented in this finite horizon module, and in particular, the function is called finite horizon DP. And it'll return a whole bunch of things. It returns, but the most important things it returns are the reorder points and the order up 2 levels. So in these finite horizon problems, if you have a fixed cost, an SS policy is optimal. And if you have no fixed cost, then a base stock policy is optimal. But the base stock levels or reorder points or whatever can change from period to period. So this function is going to return a list of reorder points and order up 2 levels. And if you didn't give it, if the fixed cost was 0, then the reorder points are going to equal the order up 2 levels. That's what makes it a base stock policy. Okay? So that logic isn't enforced in the algorithm. It's just that the result of the algorithm is that these policies get followed by the optimal solution. So here's some code to do that. And let's run this one. So for example, I'm first specifying all the data and running the model. And this is saying that in period 1, little s is 110 and big S is 133. And that's the same for a couple periods until the last period of the horizon, when little s is 111 and big S is 126. If instead we set the fixed cost to 0 and rerun it, we should see that the reorder points at little s and the order up 2 levels big S are equal to each other, and indeed they are, 133, 133, 126, 126, etc. Okay? This function has to do some truncation and discretization. So this is a dynamic programming problem, and when you just write it on the chalkboard in class, you say things like, for any possible starting inventory level, we calculate the following. But of course, we can't really do that in code for any possible starting inventory level because there's an infinite number of them. So if the demand distribution is continuous, we have to discretize. And either way, we also have to truncate the range of possible values that we consider. And in the code, I tried to be careful about this in like the default parameters. But if my default parameters aren't good enough, like because, for example, you think that the actual value, the actual optimal base stock levels are bigger than the range that my code looks at, you can set those through some of the parameters that the function gives you. So the reason this function signature is so long is that there's a couple of extra parameters here that just let you, adjust those. Okay. Okay. Any questions about single echelon inventory at all? Okay, great. So what I'm going to suggest is that we basically skip section 3, which is on supply uncertainty. So this section has EOQ models and news vendor models with disruptions and yield uncertainty. But the mechanics of how you run them and solve them is very much like what we've already been doing, so let's just skip that and you can read it on your own. And instead, let's go to section 4 on multi-echelon inventory optimization. Okay, so let me make sure this is run here. All right. So the multi-echelon inventory stuff gets more complicated because you can't just give it like a holding cost, a stockout cost, and a demand distribution. You have to tell it those things for multiple nodes. The functions try to be flexible about how you do that. So in some cases, you can just say, okay, here's a list of all the holding costs, here's a list of all the demand means, and so on. But another way to do it that's more flexible is to create an object that represents your whole network. And that's useful in the multi-echelon inventory optimization, and it's especially useful in the simulation stuff that, as I said, I'm not really going to cover today. But these two classes let you build a supply chain network. So you have supply chain nodes. Oops, sorry. You have supply chain nodes, which give lots of data, whatever data you need about the node, and then you can link those nodes together into a network. So for example, this code says, okay, maybe I'll make that a little bigger. This code says, all right, I'm going to build a node. So I'm going to build a node that I'll call my node. And it's a supply chain node. It's going to have index number 1, a local holding cost of 3, a stockout cost of 20, and a shipment lead time of 2. And I'm going to build another node called my other node that has index 2. You're allowed to give it like a text name, so I'm calling it other node. And the only data it has is an echelon holding cost of 1.5. Okay? Why you would want these particular sets of parameters, I have no idea. I'm just trying to demonstrate that it's flexible about what parameters you give it. You can't just give it any old thing. There's certain parameters that it knows how to interpret and certain that it doesn't. And the documentation lists all the different parameters that you can give it. But for all the functions I'll talk about next, it uses various combinations of these parameters. So if I run this code, now I have 2 nodes, my node and my other node. And now I can combine those nodes into a network. So first I'm going to create a blank, an empty supply chain network called network. And then I'll add my first node to it. And then I'll add the second node and say, this is going to be a successor to the first node. In other words, this node is going to be attached downstream from the first node. Okay, so now we have a network object that has a directed edge from my node to my other node. And you can now query these, like you can get data back from these nodes. So I can say, all right, give me the first node in the list of nodes. I'll call that N1, and tell me what the index is for N1. That's node 1. Tell me what the holding cost is for node N1. Okay, it's 3. Now get me the node that I told you has index 2. So like, if you access the nodes this way, you're basically just going in whatever order they happen to get stored in the list internally, which is often not really that predictable or meaningful. But you gave it indices for these nodes, and so you often want to say, all right, for node 2, node with index 2, get that node, and then tell me what its index is. It better be 2. Yep, it is. Okay, and now tell me what the echelon holding cost is. It's 1.5. All right. So I built this network quite manually. I built a node, I built another node, and I said attach the nodes in this certain way in the network. But there's lots of functions in Stockpile to build common kinds of networks. So if you want to build a single stage network, that's really just one node. Node and stage are interchangeable here. That's really just one node. You can do that with this function called single stage system. It's not that useful for the features we've talked about actually, but it's useful for simulation sometimes. There's a function though that is more useful called serial system. So serial system lets you just specify the data and it builds the nodes and attaches them in a serial system without you having to do it manually. And there's several different ways to specify the data, to specify the lists. I won't go into the details about that now. Just like before, it's meant to be flexible. It's also maybe a little bit of overkill, but oh well. So in this code, I'll build that network. It's index 210, and the holding costs are 742, et cetera. So I can build this, and now I have a network that has 3 nodes, and I asked it, okay, give me a list of source nodes. Source nodes are nodes that have no predecessors. There's only one source node, it's node 2. So the 0th element of the list of source nodes, and then tell me the index, and it equals 2, as expected. Or I can say, all right, let's get the middle node. So the middle node is the 0th source node, that node's successor. Get a list of successors, and it's the 0th successor, and now tell me the holding cost. That's not the only way to access that node. If you know the index of the node, you can just grab it. But you can also sort of iterate through the nodes in a way similar to this. Okay? All right. There's functions to calculate OWMR systems, which is one warehouse multi-retailer systems, or multiple warehouse one retailer systems. Those are like assembly systems with multiple upstream nodes and one downstream node. There's a very general function called network from edges, where you just give it an arbitrary list of edges and it connects the nodes appropriately, like for something like this. Okay, we'll skip all of that stuff. And one other thing I'll mention is that in addition, there are a lot of like built-in instances in Stockpile. So many of these are from our book, some of them are not. But for example, you can just load the instance called figure 614, because this is figure 614 in the book, and Stockpile already knows what figure 614 is, so you can just build that network in one line by just loading that instance. And there's maybe 70-ish instances built in, that you can just load like that. So partly that makes it easy if you're specifically using the problems in our book, but partly also it's just so that if you want to play around with like, how does this function even work? You don't need to do something like this just to build the network. You can just build, some simple network in one line. Yeah. Okay, the question was, can you change the inventory policy for each echelon? The answer that's going to make you happy is yes, but the answer that's going to make you sad is that will have no effect for any of the optimization, but it will have an effect for simulation. Like, the inventory theory even for optimization, I think I'm right in saying, couldn't solve a serial system where one node uses a base stock policy and one node uses an RQ policy and one, right? So I couldn't optimize that, even if you gave me that data. But I can simulate it. That's easy to simulate. So that kind of thing is very possible in the simulation component. Yeah, I'll show you in a second what the different functions are and what they do. But most of them, I think maybe all of them assume a base stock policy. Yeah, thank you.
We have a fixed source and fixed destination, and between these two nodes, we have different types of distribution networks. And let's say we want to, there are 5 scenarios that we can build. So just I'm trying to get it correct. Can we run this network of nodes with two fixed source and destination nodes with a couple of nodes intermittently which we can vary to flow through the serial system to kind of get a optimal network that would
Let me make sure I understand your question. I think you're asking, suppose you're considering several different network structures. You have a source node and a sink node and then a couple different possible arrangements in between. Could you optimize each of those separately and then pick the best one? Yeah, the short answer is yes. The longer answer is, but I mean, this code can't just optimize anything. So if you're trying to optimize something that we don't have, that Stockpile doesn't have a function for, which partly also means that all the inventory theorists in the room haven't yet figured out algorithms for, then it can't really help.
So we have to define the sequence, get Stockpile to be run in the loop, and then propagate.
Yes, exactly. Okay. So, all right. So the code has functions to, all right, we'll skip that. The code has functions to optimize serial systems under the stochastic service model. So this is the Clark scarf type approach, and it's basically like a bunch of news vendors in a sequence. The news vendors can have stockouts, And what makes this a difficult problem to solve is that, in a serial system like, sorry, I need a picture. In a serial system like this, node 1 is ordering from node 2, but node 2 gives a stochastic lead time to node 1, right? Even if the transportation lead time is deterministic, node 2 is sometimes going to have stockouts, which means that the effective lead time that node 1 sees is stochastic. And that makes multi-echelon inventory much more complicated than single echelon inventory. And there's basically two different ways of coping with that. One is this stochastic service model approach. The other is the guaranteed service model approach. So in the stochastic service model, we have a much more, we meaning the world, has a much more limited set of types of problems we can solve. Serial system is the easiest. So we can solve a serial system in Stockpile. Here's an example. And this is basically running Clark's scarf, or like the newer kind of incarnations of it. And so here are the optimal base stock levels, and here's the optimal cost. There's a couple different ways to build the system, to pass in the data. I'll skip those details. There's also this news vendor-based heuristic by Shang and Song that solves the same problem, is much, much faster to solve and very, very accurate. So I also implemented that. Uh-oh, what did I do wrong here? Oh, wait. That's because I skipped some code here. That's okay, we'll just skip that. So we have the news vendor heuristic implemented as well. And you can compare the costs of those solutions. Now, the world of SSM models, Clark's scarf type models, kind of ends there. I mean, we can solve assembly systems, but the policies are sort of weird. There's certain things we can do in distribution systems, but we can't just solve really general systems. There is more that I still mean to implement in Stockpile. All I basically have is serial, and I'd like to do more because there is more out there. But SSM models just can't get that general. GSM models, on the other hand, can get much more general. And if you're familiar with these models, the basic approach is you have to bound the demand. You have to say above, let's say, 3 standard deviations above the mean, we just pretend the demand can never be bigger than that. And that lets you put a bound on how big those lead times can be among the nodes. And it makes it computationally much easier. And as a result, we can solve much more complicated problems, much more complicated network structures. The downside is you have to do this demand bound, which is kind of, not satisfying. And also these models, instead of optimizing base stock levels, they optimize these things called committed service times, which are one-to-one with base stock levels. So you are basically optimizing base stock levels, but it's a weirder kind of concept in practice, especially to try to communicate. In any case, Stockpile has functions both for serial systems in GSM, under the GSM model. It solves it using dynamic programming, and also for tree systems, basically any system that doesn't have a cycle. And that can be solved with this dynamic programming algorithm by Graves and Willems from 2000. So I implemented that. Okay. Now, we still would like to be able to solve general multi-echelon inventory optimization problems, but there's, the theory hasn't caught up yet. So I wrote a couple of functions to basically optimize these things with brute force. And I will just warn you now, they are terrible. They're both really slow and really inaccurate. It's like the worst of both worlds. But if you have a system that we don't have theory on how to solve, like maybe this kind of approach is the best kind of approach. So there's essentially 2 different ways to do it. One is enumeration. So you give me a network with, let's say, 5 different nodes, and you tell me all the different base stock levels that you want to test for each node, and I just enumerate all the possible combinations. You understand why this is really slow. And then instead of enumeration, we can instead do coordinate descent, where we're just optimizing over one decision variable at a time. And then within each of those, there's two things you can do to just evaluate the cost, right? Because part of the problem in inventory theory is often, if the system is complicated enough, we can't even write down a formula to optimize, to express the cost. We can't write down the objective function, in effect. So you have two choices. You can either give it that objective function explicitly. If you know the objective function, the cost function, you can code that as a Python function and just give it to my function. And then when I do my enumeration or my coordinate descent, every solution that I want to evaluate, I call your function to do it. Or you can estimate that cost through simulation, using the simulation features that are in Stockpile already. But now, in addition to having to do like enumeration, which is clunky, now adding simulation, which is also slow and variable, I mean, it's definitely not ideal. But as I said, for some kinds of problems, this is the best we have. So, and these can be very slow to run. You have parameters you can control to tell it like how many simulation runs, how big a range of values do you want to test, to try to get an okay, balance between the execution time and the quality. But it's just really, really slow for anything but really small problems. But if you want it, it's there. Okay. All right, that's it. Ebru, you asked me to save 5 minutes, and I did. Okay. Any other questions? Thank you all for asking questions during, by the way, but any other questions?
Can you change the distributions, like demand distribution or lead time distribution? And also, second question, can we consider the supply uncertainty?
Yes.
On the vendor side.
So demand distribution, yes. There's lots of ways to change demand distributions. It's a little different for single echelon versus multi-echelon and so on. For simulation, that's the most easy and flexible. You want to simulate any kind of system with any kind of demand distribution, that's easy. But again, like I can't optimize certain kinds of distributions, so I didn't, so for some functions, you can't be quite as flexible. Lead time distributions, no, because I don't have any features for handling stochastic lead times yet. Maybe in the simulation I do, I can't remember. And then the third question was supply uncertainty. Yes, I have a whole section on supply uncertainty, but that's only single echelon, like EOQ with disruptions kind of thing. In the simulation part, you can simulate supply uncertainty, like disruptions within your supply chain network. But there's no multi-echelon supply uncertainty optimization in the package. Partly because there's very little literature on that to begin with. Other questions? Thank you.
No, I just want to say that very impressive. The amount of work that goes into doing all of this is just tremendous.
Thanks, Anna. I appreciate that. I mean,
thank you.
I would not have done it if I didn't love this kind of coding and all the documentation and everything. Like, I found it really fun and also really frustrating in certain ways, but I got over the frustrating part. So thank you for saying that, and also, like, I just enjoyed doing it, so I did it.
And as I told you at the beginning, that my students are really enjoying this right now.
Good.
Yeah.
I'm glad.
This is just a broader question about inventory theory, not necessarily about the package. Is there any theory around inventory optimization when you have aggregate constraints? Like, for example, you have N SKUs within a warehouse, but you can only hold Y units overall. What's the best mix of them?
There's probably people in this room who are better answering that question than I am, but I'm going to do my best and say, I think from an exact optimal point of view, there's not that much literature on that. Problems like that tend to rely on heuristics because they're more complicated to optimize. So I think there is some literature, but it tends to be heuristic and a bit more ad hoc, as opposed to these much more well-defined, codified kind of seminal models that is what's coded in Stockpile for the most part.
Okay, thank you.
Thank you.
Thank you very much.
Okay, thank you all. Appreciate you being here.